Murakami-Murakami. Okay, so this is 97 and 2001. So because Chen has already tell you what is the volume conjecture, but because I want to also study the colored SU and invariant and also super polynomial, so my notation will be a little bit different from the standard notation introduced by Chen. So here is the original volume conjecture. And yeah. So here, Q equals e to the pi I. I use the simple pi I over R, over N. And then this is take the logarithm, take the absolute value, take a limit, and goes to infinity. It's volume minus K. So here, here the n is a bit different from the standard notation. Here n means the large n, capital N means we have n box for Young tableau. So this n means we have n box of Young tableau. So here I want to emphasize the Young tableau because the later work will also depend on those Young tableau. So this is n box of Young tableau. So it means the symmetric power of n, and we take the fundamental representation V2. So the dimension of the symmetric power of n of V2. So it is dimension n plus 1. So here we use n plus 1. Okay, so we choose the correct root of unity. This is the correct root of unity, the pi I. Only we take the pi I. Here we take the q to the n minus q to the negative n over q minus q inverse. So this is the definition. So actually in many physics literature, they use the q to the half n minus q to the negative half n. So you should use the 2 pi I over n plus 1. But here I use pi I, e to the pi I over n plus 1. So actually they're the same. Okay, so then, so people may be curious about this root of unity. Why only this root of unity works, give you the exponential large, and instead of polynomially large, and also give you that the exponential growth rate is proportional to the volume. Why we choose this specific root of unity? And after a lot of computation of other quantum roots of unity, other quantum invariants, so we find this kind of chosen root of unity is closely related to the so-called the cyclotomic expansion of Hyperbolic type cyclotomic expansion. So here is Hyperbolic type. Hyperbolic type cyclotomic expansion. So his result, I first give you some examples. So about J1 of Q, K, is 1 plus here H1, K, and here is 1, and here is 3. So what is this J1? So J1 is our older friend. It's the original Jones polynomial, okay? Because J1 means we have only one box of the Hyperbolic box. So it's just the fundamental representation. So the J1K is 1 plus H1K. H1K is a coefficient. So in this polynomial ring, integer polynomial ring. And 1 and 3. So what is 1 and 3? So this is also kind of notation. This notation. And what is like n? Q to the n minus q to the negative n. So this is the basis 1 and 3. And the second, so J2 is 1 plus H1K 2, 4, and plus H2K 1, 2, 4, 5. This is the basis. This is the basis. This is a Hyperbolic cyclotomic expansion. And Hyperbolic proved this result until Jn. So Jnk is 1 plus like H1k n plus 2 until the last one is Hn. K, what's the basis? Is 1 until n, and n plus 2 until 2n plus 1. Okay, so this is Hyperbolic's result. So it said so for any not k. So this k is not any not k. It exists such kind of hi in this polynomial ring, integer polynomial ring. Then we have such kind of expansion. Okay. Okay. Yeah, it's clear.
On the stage.
Oh, on the stage. So you can determine those HIK recursively. So from J1 you can determine H1, right? After you fix H1, here H1 is fixed, then you can determine H2. So from J2 and H1 you can determine H2, right? And from Jn and H1 until Hn minus 1, you can determine Hn. Right? So this is a recursive way.
What is your normalization here?
Renormalization is like a J0 is 1. So normalization is J0 is 1.
Then you cannot have n in there. I mean, in that
Where?
cyclotomic expansion. Yeah, you cannot have n in the middle.
This n.
Yeah. And
This n means n plus 1 dimensional. It's not this is n plus 1 dimensional. Not n dimensional. This is n plus 1 dimensional. So here n and here n plus 1. So this means n yang tableau. So this is n plus 1 dimension. So dimension is
your n is the dimension. Okay.
Yeah, n plus 1 is dimension. So n is the number of the yang tableau.
Okay.
Yes, yes. So this is so now it's very interesting. You see, if you have Jn, okay, if Q equals e to the pi I over n, this is the same as Jnk e to the pi I n plus 2. This is 1. So it is just 1. You see, if you are plugging into the any other root of unity, maybe n plus 3, n minus 1, it's not only polynomial growth. It's not exponential growth. Only the root of unity in this gap. So only the root of unity in this gap. You see, there is a gap here. So n to n plus 2. So we solve the gap equation. So what the gap equation is n plus 1 equals 0. Then you get q to the e s pi I over n plus 1. This is the correct root of unity for the volume conjecture. So here we find a very close connection between the cyclotomic expansion and the volume conjecture. But actually, the volume conjecture is discovered by Kashaev much earlier than the Hyperbolic's cyclotomic expansion. But actually, they have a very tight connection. So that means each time, if we can find the cyclotomic expansion structure for any quantum invariants, then we can find the volume conjectures. Actually, I did this with my collaborator. We did this also for colored SUN. also for the super polynomial with categorification. We all find the cyclotomic expansion, and then we find the volume conjecture, and we can prove the figure 8 case. So this is the first direction of generalization of the original volume conjecture. And the second road of generalization of volume conjecture is my work with Tian Yang. We propose the conjecture, and then we can do a lot of examples. So there's two types of generalization. So this type is we go from the Carrot-Jones to Carrot-SUN to also to the super polynomial. This is one direction. Another direction will go from the knot complement and the link complement to the three manifold. So for shifting to life and to 0. So this kind of generalization is still for knot complements and the link complements. It's not for three manifold. Yeah, so it's still for like the Caspar manifold.
I have some, if Q is not a root of unity, but Q is a number whose absolute values
Yes, they also have some generalizations. Yes. This, if you consider the Carrot-Jones polynomial and it have other kind of root of unity, I think Hitoshi Murakami, he has some results for that. In his talk, I've heard his talk several times. Okay. So now, I'd like to here introduce the Carrot-SUN. Carrot-SUN and invariant. So we propose some conjecture. So this is not approved yet. So there's some conjecture with Qifeng Liu. He's a professor at the UCLA, and his former student Shen Maozhu. Okay. So this conjecture is like we have a J1 SUN. Okay, the 1 plus H1 N. Okay. N. So you see, here is a 3. So actually, this is Carrot-SU2, right? So Carrot-Jones is SU2 invariant. SU2 invariant here is 3 is 2 plus 1. You change to SUN, so it's N plus 1. This is cyclotomic expansion. And then J2 SUNK. So here I want to mention, so Nawata also gets some similar results of this part. the cyclotomic expansion. 2 and N plus 2. So it's go from N plus 2 to N plus 3. And the conjecture is like, it's very similar to this one. So J N SUN K equals 1 plus H1 and K. Here is a N plus N until H and K. Here is 1 N plus N until 2N plus N minus 1. So this is the cyclotomic expansion conjecture. So also for any knot K, there exists the HI K inside of this polynomial. So this is our conjecture. And then you look at those gaps. So the gap is enlarged, right? So here the gap is only there's only one gap. But here the gap is enlarged. What is the gap? So the gap equation is here. So the gap is here. So here and here. So this is the gap. So all the gaps is like I can write M plus A equals 0. So what is A? A is from 1 to n minus 1. So previously, because n equals 2, the small n is 2. Small n 2, we consider the Kashaev-Jones polynomial. Kashaev-Jones polynomial, small n is 2, so we have only one gap, right? So A can only be 1. But now, if we consider SU6, A can be have 5 choices. So 1, 2, 3, 4, 5. Have 5 choices. And then we solve the gap equation. So any root of unity like this, e to the pi I x pi I over n plus a, can be the correct root of unity for the volume conjecture. And then we make the volume conjecture. This is a volume conjecture. And so equals the volume. So this is the new volume conjecture. So A from 1 to n minus. And we can prove the 0. What?
I think it's better to put
Oh, yes,
on
yes.
the stage, I guess.
Yeah, so this is a colored SU and BC is true for figure 8 knot. So we can prove this result.
And we use explicit formula for figure 8.
Yes, of course. Specific.
But where is the another proof? I mean, I know that there's some conjecture about even for figure 8.
Figure 8, if we have a Young tableau of a row of Young tableau,
Yes.
this is not obtained by physicists, it's by mathematician. The paper is in the intelligence in Kyoto University, intelligence conference. So Ozuki, he gave me the original paper. So Kawago, I think by a Japanese mathematician. This is not a conjecture. So for figure 8 of SU, colored SUN, only with one row of Young tableau, this is not a conjecture. It's a 0. Yeah. What?
What do you mean by volume?
The volume S3 minus K, the volume. The hyperbolic volume here.
The same as there.
Same as there. The same volume.
But if you consider SL2, then it makes sense. Because SL2 is the isometric group. But here,
Yeah, SUN, but we get the same result.
hyperbolic.
Yeah, also hyperbolic volume, same. So Francis previously asked the same question when I gave a talk, but Francis had some explanation. Can you repeat, Francis?
It's because single row.
What's hanging in the background?
I'm playing with my computer.
It's a homology class. It's a three-dimensional homology class in SLN. So it's these ideas of Walter Neumann and Christian Zipper. Okay, this bigger talk. You expect, but for SLN, SUN, you expect three-dimensional hyperbolic volume, not in n-dimensional.
But multiplied by a cubic polynomial of capital N.
With the power, perhaps.
Yeah.
With the power, yeah. I actually, Star Wars, you know that.
Maybe physics
Star
comment.
Wars is a much better reference.
Maybe physics comment. It's because he considered only single row in the Young tableau. So if you SUN, there is a freedom to go to the width, like the depth of the Young tableau. If you consider arbitrary Young tableau, the volume would change. volume part will change. But he only considers single row. That's the reason.
You can discuss more. I need one more minute.
On the right-hand side, there's no dependence on small n. I cannot be conditional. So if right-hand side has volume also dependence on n.
There is a large n.
Small n implicitly come from here. A depends on small n.
Yeah, good. Yes.
Till up to n. So then a small n, the freedom small n appear here. That's only appearance in small n order.
Yeah, so this is two theory is very parallel. It's very just parallel to the current Jones. And so now I will show you the super polynomial case. The super polynomial.
Should I get rid of this one?
Okay, thank you. So previously I want to also cyclotomic expansion, and we previously studied some so-called Lavastia-Marino-Uguri-Waffa conjecture. This has some connection to the open global theory. So this is our starting point, it's our motivation. So here I can explain a little bit here. So this is like the building, the whole building of the quantum invariants. So this is the first floor, the ground floor. The ground floor is like here. So you have fundamental extension, UPSL2, so you got the Jones polynomial. And then Humphrey and Kaufman. This is a classical word. And this is a quantum word. So it's current Jones, current Humphrey, current Kaufman. So those are obtained by Rashidin and Tulayev under the idea of Edward Waiter. And so here is some three secret tunnel to the other branch of mathematics. So here is a hyperbolic geometry. So this is the first secret tunnel. So about the original volume conjecture. So it's proposed Kashaev-Murakami-Murakami. So hyperbolic geometry. And those two direction is to the open global frequency theory. So we call it the large n duality. It's large n duality. So this Lavastida, Marino, Uguri, and the Waffa conjecture. So the original conjecture was proved by Kifonglio and Pampen. So this is my part of my PhD thesis about 10 years ago. So it's orthogonal MOV conjecture, but we proposed the conjecture, we proved several interesting cases, but we know that this conjecture is still open. And this work, the rigorous work of the orthogonal MOV conjecture is based on the work of some work of Belyakova and Blanchet. So they have for the orthogonal LMOV conjecture. Okay, so this is our motivation. We studied those LMOV conjecture and got some congruence relation for the current Humphrey invariant. For the current Humphrey, then we go to the current SUN. So this is our motivation. It's too much, so I'm going to skip. And here is so we got some congruence relation, and the congruence relation is from the cyclotomic expansion. From cyclotomic expansion, we can get some congruence relation, and from congruence relation, we can get some symmetrical results. This is give a new proof of Professor Luss' results about 20 years ago. So this have symmetrical property. So this is for current Jones. For current Jones.
This was Kirby and Melvin, it's not mine.
You're not here.
I generate this to SLN.
I think Kirby, Melvin, they don't. I think they only have this part, not this part. They have, I think, one side, not both sides. So both sides is probably still your work, because Kirby only gives some examples. They didn't write it as a theorem. They give some like a test of examples. Only half of the half of this side. So and then here. So this I give a quick comment of the volume conjecture. So the volume conjecture, the current status of the volume conjecture, the Japanese school contribute a lot recently. So they prove a lot of cases. So previously, after the volume conjecture was formulated, the figure 8 case was quickly proved. Alcohol quickly proved the figure 8 case, even he don't write a paper. It's very simple. So, but the second case, second hyperbolic knot case is the 5-2. So this is very difficult. So by a series attempt by Yogoda, Kashaev, and also Otsuki, so finally we have a complete proof. So the alcohol give the proof of volume conjecture, and then Yoga, Anderson, Hansen give a full asymptotic expansion. Then Otsuki, he proved by analysis method. So a combination of Poisson summation formula and the saddle point method. It's a very complicated method. So his paper is about 80 pages. Then so Otsuki, oh, sorry. Yes. So I should page down, not the page. Yeah, so this is the method. Sorry. So by careful analysis of combination of Poisson summation formula and the saddle point method, and you can prove 5-2, and then Japanese school learned his method quickly and proved several more cases, and we got stuck again because this method is very powerful, but it also has its limit because it became very complicated when you needed to check a lot of conditions for how you can use the Poisson summation formula and the saddle point method. Actually, and some quantum topologists, they question the method of saddle point method. So they think it's not rigorous. Actually, this is rigorous. This method was applied by Riemann 150 years ago, but currently only physicists use this method without check any conditions. But Otsuki, he check all the conditions required by the saddle point method. So this method is rigorous. But you needed to check a lot of conditions instead of directly applying the method. But the physicists directly applying the method, so maybe it's not that rigorous in the view of mathematician. Okay, then we have some remarks. So also has some physics meaning. So it's given by Gukov and Witten. So for the volume conjectures. This is colored SUN. So colored SUN have a lot of definitions. This is one of the definitions from the colored Humphrey invariant. Then we have some congruence relation conjecture, and this from the if you admit the congruence relation conjecture, we check some examples. Then you can get the last result. I think this is your result. Yeah, that's the A, and so that's the root of unity of positive 1 and negative 1, and for such kind of root of unity. And from this we can get so this is our motivation to get the cyclotomic expansion. So I already write here. This is a conjecture. It's parallel to the Hyperbolic theorem. The difference is we propose a conjecture, not a theorem. And here is the volume conjecture for colored SUN. So this is volume conjecture, and we prove the figure is not. So
sorry, for the figure 8, can you prove your cyclotomic expansion?
Yes.
You also can.
Yeah, because it's very easy. So the coefficient. So we put the paper on the archive. So several years ago. So this is the proof is very simple. Just directly from the result. And here is the cyclotomic expansion for super polynomial. The super polynomial is given by two groups of people. So Danfeld, Gukov, and Rasmussen, and first given by 4 physicists, and then mathematically they give a rigorous proof, and also reformulated. So this is a super polynomial. So super polynomial is so I want to point out this T. So what is this T? This is a categorical variable. So when T equals -1, it's decategorification. It go back to the Colored-Jones. So it's like here. So when you take the -1 and then A equals Q squared. So this is just Jones, our old friend. Okay, this is our old friend, and this is the cyclotomic expansion. So all the coefficient is 1.
But formula is still conjecture.
What?
Formula is conjecture.
This formula is conjecture?
Yeah, yeah.
I don't think so.
Who proved that?
I think Rasmussen, they proved that.
I don't think so. This is colored, right?
Colored.
Color, but recently differential on Hornfley PT of colored Hornfley PT is given by really recent, by Curtis.
By Curtis.
Yeah.
Okay.
So this is conjecture. This is conjecture.
But this is recently proved, I think, by the recent paper.
By whom? Anyway.
I think for figure 8 is proved. Maybe not all the twists not.
Okay.
The figure 8 at least is proved. And also torus knot is also proved. Torus knot. So this is our conjecture, the main conjecture for the super polynomial. So super polynomial, I introduced a new byproduct, the alpha k. The alpha k is a new byproduct. So after you adding this new additional term, it also can have some cyclotomic expansion. And I checked all the computation from mathematics and physicists, all the formulas. So this conjecture set is satisfied. So this conjecture can be understood in this way. So alpha k is a byproduct. So if n equals 1 is true, then the alpha k is fixed. Then you check the conjecture for n equals, the capital N equals 2 and 3 and 4 and 5 later. So if n equals 1 is correct, then you fix the alpha k. And finally, we find a lot of similarity from this alpha k and one of S invariant, and also the Oshua-Szabolcs knot floor tau invariant. So this is S invariant and tau invariant. So this is we find this torus knot Tm(n). We find that the alpha invariant equals negative n minus 1 n minus times n minus 1 over 2. This is closely related to the Milnor conjecture. But here is the Milnor conjecture. The relation to the smooth four-ball genus. Here is the definition of smooth four-ball genus. So it's the minimum genus of a surface smoothly embedded in the work in the four-ball B4. And then it's called a slice knot if the smooth four-ball genus is vanishing. So previously, a lot of famous topologists have made a lot of contribution to the smooth four-ball genus. So like Michael Friedman, so he has several nice theorems about the smooth four-ball genus. And so this suggests a very close relation to the Milnor conjecture. Milnor conjecture is like this. So smooth four-ball genus is given by this one. And it is first proved by Kashaev-Murakami, and then later it's proved by Rasmussen. So Rasmussen introduced the knot invariant Sk from the Hovanov homology with a lower bound of the smooth four-ball genus. So Rasmussen is 0, Sk smaller than 2 times G4K. And then use this method to give a second proof of the Milnor conjecture. And here we make a conjecture so my invariant alpha k is also a lower bound for the smooth four-ball genus G4K. And have this one. And for all the knots we tested up to 10 crossings, it is identical to the Rasmussen's S invariant and also my Szabolcs tau invariant. I mean here you have just alpha k over 2 is the Sk. So this identical means is up to a 2 factor, and exactly equals to the tau invariant. So actually previously we have a conjecture given by Rasmussen. Rasmussen has a conjecture because he tested a lot of examples that S invariant is equal to the tau invariant. But finally Haydn gave a counterexample to the S and the tau invariant. They are not equal to each other. So this is the new situation. So my alpha invariant up to 10 crossing is also equal to the S and the tau invariant. But we don't know is there any counterexamples after 10 crossings. So it is possibly, so this alpha invariant maybe it's equal to the S invariant always. Maybe it's weaker than the S invariant, maybe also stronger than the S invariant, we don't know. So we need to test more examples. At least up to 10 crossings, I checked all the results. So it's identical to the S and the tau invariant. So you can see here the S invariant. So this is some result for the S invariant. So and the H1K. So you see here so I check all the so-called the homologically thick invariants, knots, homologically thick knots. So 8, 19, and then 942. So you see here. So S invariant for 942 is not sharp, and my invariant is also not sharp. So all the others, but up to 10 crossings. Because for the alternating knot, quasi-alternating knot, I don't need to check. It is I prove 0, so it's always like the sigma. It's always half of the sigma. Sigma is the signature of the knot. Signature. This signature smooth homogeneous S invariant and my alpha invariant. So you can see always identical to the S invariant here. So this is all the homologically thick knot up to 10 crossings. So now I want to encourage you to complete some more difficult examples. Maybe, hopefully, I have only maybe 20% of hopefulness. So my alpha invariant may be stronger than S invariant. Maybe, I don't know. Because S invariant is from Hovanov polynomial, and tau invariant is from not floor homology. But alpha invariant, this alpha invariant is from the Hovanov-Rosansky. It contains more information, because Hovanov-Rosansky contains more information than the Hovanov, right? Because it has the SUN. So hopefully my alpha invariant also may contain more information than S invariant. But this is just my hope. I don't know. Okay. So then I want to show you some very recent results with my mentor at ETH in Switzerland. We got some new results for the so here the new result is here. For the double line, so for the double Young tableau. So this is our paper. So I haven't finished with the details, but we have obtained some results. So this is the new volume conjecture for the Young tableau with double line. So I mean, the Young tableau with double line is like this. How many minutes do I left?
10 minutes.
Only 10 minutes. So here is we consider such kind of Young tableau by NP. NP. So this is.
There is no way we can see the ball.
Oh. So this is just the Young tableau, yeah, N by P. So the N by P. So this is the volume conjecture becomes very interesting in this case. So it's not converges to volume, but P is involved. So I give you some sense here. I consider SU4. SU4 by N by 2. So such kind of type of Young tableau, the rectangular type of Young tableau. So we have volume and double volume and volume. This is also has close relation to the cyclotomic expansion. But the cyclotomic expansion for this one is more complicated. But actually, we prove the result for figure 8 for all this type figure 8. But maybe the formula we obtained is from the physicist. But from the physicist formula, so we can prove the result for the figure 8 knot, for figure 8. And this is very mysterious. Why it's double? So the A equals 2, 1, 2, 3. They're different. The structure is very subtle for the rectangular box. Okay, we can also prove the case here. For figure 8 knot, we can prove all this, not only this. For figure 8 knot, we can prove all of them. So this is the work of my work with Giovanni Felder and also Huafeng Zhang. We are both postdoc of Giovanni Felder. So this is the conjecture. Okay, so now we go to here the another direction of conjecture, my conjecture with Kenyan. So this conjecture, I just because I don't want to repeat. So, and also we make some conjecture for Q order. Okay, so here I want to I give a counter for how many examples for the Kasparov manifold. So for tribe 0. For tribe 0 case, so previous Kasparov-Jones polynomial. Previous Kasparov-Jones polynomial only proposed for those knots. For if you use 8 tetrahedron, that for the ideal triangulation, for 8 tetrahedron, you only, the original volume conjecture only proposed for 299 cases. And my volume conjecture with 10, so we have proposed for orientable Kasparov manifold and non-orientable Kasparov manifold, or even manifold with totally geodesic boundary. The boundary is genus 2 or higher, even higher. So you have, but this is included. This kind of example is included in this category. So we propose all this category. So this is the Giseki manifold. The first one is Giseki manifold. So it's a non-orientable manifold. So you identify all the 6 edges to one edge. Okay, so in the tribe 0 case, we witness very dramatic cancellations. So I will mention later. So this is the Giseki manifold. And so the approach to the volume. So this is still open case. The cancellation is very dramatic. So why we call it quantum invariant? You see here. So we witness very drastic and a huge cancellation for the figure 8 knot. And figure 8 knot finally is proved by Dedetrier, Kafjani, and Yang. And but if you want to search for direct proof without establishing some formula with Kasparov-Jones, without establishing the formula with Kasparov-Jones, it is still open. So if you want to give a direct proof, so because it's a huge cancellation, we cannot control the huge cancellation. And so this is very different from the original volume conjecture. Original volume conjecture, we don't have such huge cancellation. So here we have a huge cancellation when we do the asymptotic expansion. So this is my starting point of my work with recent work with Qingtao Chen. So here, before I introduce Qingtao Chen, so here is some recent result of. So I think Yang has already given some account for this part. So I can skip this part. Okay, so that's because I only have 5 minutes. So I just so this and some physicists, including my advisor and Zhenhan Wang, they point out this should be a non-unitary theory. This is some physics background. I also asked Kashaev, he also told me this should be non-unitary. I think the non-unitarity is from this one. From the quantum integer. It can be negative. Previously, the quantum integer is only positive. So this is the point out it's non-unitary. And here is my work with Murakami. So this is some. So one hyperbolic, so tetrahedron. So the quantum 6 symbol give you the hyperbolic volume of the single tetrahedron. What?
Is it true for all the hyperbolic?
This conjecture we proved I think 80% of the case. So because we need at least we need to assume at least one vertex is ultra ideal. So we prove this case is when so here we show that the above conjecture is true for T is hyperbolic, and at least is one ideal and ultra ideal vertex. So this is I think is not the whole case, but the majority of the case. We didn't prove for all the cases. So that's why I list here as a conjecture. Because we prove only majority of the cases. And also we prove a theorem, so that is with one vertex ideal and ultra ideal. And not only the dominant term, but the second dominant term is related to the grand matrix. So this is the dominant term. Here is the dominant term. And this term we also prove. This is the secondary term. Secondary term. And then third term, fourth term. How about the behavior of third term, fourth term, fifth term, and like those small terms? Actually, they're all identical to each other. If we change the dihedral angle from positive to negative, we change the sign of one dihedral angle from positive to negative or from negative to positive, then the asymptotic expansion is exactly the same. So this is our new conjecture. So before I mention the new conjecture, I give a counter here. So this is the Q Kashaev-Jones and super polynomial. So Q1 and Q2, they are almost the same. They all have volume conjectures. But for three-dimensional flavor volume conjecture, Q1 and Q2, they have a huge difference. So Q2 is the square of Q1. So all the Q1, you have only polynomial growth. So including the 6G symbol, this is a conjecture by the Woodman. It is also polynomial growth. Therefore, the root of unity Q square of the Q1. So it's all exponential growth, and we have volume conjectures. So this display a huge difference between. So for the original volume conjecture, Q1 and Q2, they are both exponentially large. But for the three-dimensional flavor, the original root of unity is only polynomial growth. So there's the deep reason behind that. I think the physics reason is non-unitary. Only you deal with the non-unitarity, you can get the exponentially large. And also you will deal with the huge cancellation. So the huge cancellation. So this is so for the specific, this is non-unitarity from here. So this can be negative. Previously, if you consider e to the pi I over r without these two, the pi n over r is always in the first quarter and second quarter. Because now you consider sine of 2 pi n over r. It can be in the first quarter, second quarter, third quarter, fourth quarter. So the sine can be negative. Previously, because in the first quarter and the second quarter, sine is always positive. So because this can be negative, so corresponding to this non-unitarity. And then here is my account. So some non-unitarity is my expectation. So this is the Witten-Chen-Samos gauge theory. From physics, you get some polynomial growth rotating triangle invariants. And it's called Witten's asymptotic expansion conjecture. It's polynomial growth. So now we discover the exponential growth rotating triangle invariants. Maybe we can discover a new non-unitarity fixed theory. So this is my comments. And here, so this is my hope. So 19th century is from linear to non-linear, and the 20th century from commutative to non-commutative. Maybe 21st century from unitary to non-unitary. Thank you.
Questions, please?
Sorry, what's Q of 1, Q of 2?
Q1 is the original root of unity. Q2 is Q1 square. So because
What do you mean? It's just Q square.
just the Q square. So Q1.
Okay.
So this is RQRS.
What do you mean unitary and non-unitary?
Unitary, non-unitary. This is
What's the definition of non-unitary?
you study the Schrodinger equation. Schrodinger equation then, because all the possibility is the wave function modulus wave function square. So the sigma sum of all the modulus square of the wave function, the sum should be 1.
Okay.
So this is unitary theory. Unitary theory and non-unitary theory, the sum does not equal to 1. So that means you can lose some possibility. The possibility is not 1. So physicists cannot admit such kind of theory.
But in the language Q,
Yeah.
what do you mean? What do you mean? I don't understand you mentioning first quarter, second, and third quarter. What do you mean?
Yeah, so okay. Because this is n. So f n at q1, it is sine pi r n. So normally you will ask n smaller than r, right?
Okay.
So when you consider the trivial theory, the sum of the triangle, the integer of triangle should be smaller than r minus 2.
Okay.
This is it's called admissible condition, like ABC, a plus b plus c is smaller than r minus 2.
Okay, that's fusion rule.
So normally, so it's such kind of a number, it's impossible to larger than r.
Okay.
So n over r is like in the first quarter and the second quarter, right? Because this is pi n over r, right? In first quarter and second quarter, so it cannot be larger than pi.
Okay.
If it cannot be larger than pi, this is always positive.
Okay.
But when we change it to the second root of unity, q2,
Oh, I see.
so this is sine 2 pi n over r.
I see.
This can be negative, because only n smaller than r is not enough to make it to be first quarter and the second quarter. It can also appear in the third quarter and the fourth quarter. So this is actually is Professor Kashaev, he explained to me why it's non-unitary, because I'm not a physicist, he's a physicist. Then I asked some physicists. So now there's it's a bigger paradox in the physics. It's called a black hole quantum information loss. They have in the black hole, you consider quantum gravity, the information loss. And Stephen Hawking also studied this for a long time. And the people already consider, if we consider a non-unitary theory, maybe we can resolve this paradox. So that's previously no physicists believe in the non-unitarity.
So T graph T is unitary if the inner product is positive.
Yes, positive, that's it.
Otherwise it's not.
It's non-unitary. So only the quantum black hole quantum information loss it requires some non-unitarity.
But for me, it's complex Chern-Simons.
Complex Chern-Simons is also non-unitary.
So yeah, I think it's better to state complex Chern-Simon instead of.
But we don't know the Q2 corresponding to the quantum Chern-Simons. We don't know that. Because I discussed, talked to Witten. Witten previously think it's just complex Chern-Simons.
Yeah.
He studied in 2010, this Q2. But finally he told me it's some new discovery. He cannot use his old theory to explain our new phenomenon. So Witten admitted this is a new phenomenon. It's not considered by him before.
Okay. No more questions. Let's thank the speaker.